All right, we're in week two. We're going to talk this week about scientific explanation. And today we're going to start off with where sort of everyone starts off when they're talking about explanation. This account was developed in the 50s, and it's called the deductive nomological account of scientific explanation. Those are some big words, but I will explain what those mean, and it will make sense. So, Hempel and Oppenheim, which is the reading that you're assigned, although also the Stanford Encyclopedia article is good if you find the Hempel and Oppenheim uh, difficult to follow. Although I found it was not the worst as far as these articles go, as far as like being written in relatively plain English. So Hempel and Oppenheim, they say, as we've been saying since the beginning of this course, one of the jobs of science is to provide explanations of phenomena. And when I say phenomena, I just mean stuff that happens, right? Um, So they begin by defining explanations roughly. And what they say is an explanation is an answer to a why question. Um, what's a why question? Well, here are some examples. You might ask, why is the sky blue? Why do objects fall down instead of up? In psychology, you might ask, why do people perform so poorly on the Wason selection task, which is a sort of little card game you give people to test how good they are at logic. Um, and people do very badly on it. So um, it's not, as we'll see later, um, defining explanations simply as answers to why questions isn't the greatest. It's, certainly you want more specificity, but it's a start, right, on what we mean by explanation. Um, Another sort of way to zero in on what we might mean by explanation is to compare them to mere descriptions, right? So I can, again, if we wanted a description of why objects fall down instead of up, I might, sort of list, well, this wouldn't be a why question, right? Uh, but I could describe sort of the phenomenon of things falling down and not up, right? And so one way to do that would just be to list all the things that fall. So balls fall down, goats fall down, helium balloons don't. Goats don't fall down when I'm in outer space, um, and so on, right? So that would, and that description could be more or less complete. I could keep going, right, and catalog as many objects as possible, but still, according to Hempel and Oppenheim, that wouldn't really be an explanation. That would just be a description, right? Um, Proper explanation, you would think, would mention the force of gravity, ideally some sort of formula that relates the pull of gravity to the mass of the Earth and the mass of the object we're talking about, the goat or the helium balloon or whatever. Um, so right, trying to sort of roughly zero in on what we mean by explanation here. Another question you might ask is, what are we explanation is certainly a word all of you know, right? If we talk about scientific explanation, is that the same sort of thing that you normally speak of when you're talking about explanations, or are they different sorts of things, right? So certainly you might ask me why I was late, right? And I could explain that there was traffic on the 5. Um, is that of the same sort of species as explaining why things fall towards the Earth using the law of gravity or not? And we'll notice that like fair amount of some of the arguments in the what we call the dialectic, the back and forth between these various authors. Some of it does kind of hinge on this assumption that explanation in everyday life is the same sort of thing as scientific explanation. And in the Stanford Encyclopedia article, that author takes issue with that assumption. Um, there certainly do seem to be explanations that wouldn't count as scientific explanations, right? So my explanation why I was late, I think everyone would agree, is not a scientific explanation, even if it is an explanation. Um, and I could explain why Moby Dick is a great book, right? I could explain why I think the Beatles are better than the Stones or something like that. Would that be a scientific explanation? I think we'd all say probably not, right? And then also we should note that in science, we do a lot of different things, and explanation isn't the only thing that science does. So you might just want to catalog all the various traits of different birds. It's not an explanation, but it's important for science. It is something that ornithologists do. Um, so again, what Hempel and Oppenheim have offered us is not exactly a sort of strict, necessary, and sufficient definition of what explanation is, but they've sort of given us some guidelines of what sort of things that do count as explanations, sort of things that don't. Um, and that can, it's useful. That can help us hone in on the phenomenon we're trying to talk about. So let's get into a little terminology here. Um, so they're going to use some sort of Latin terms that you're going to have to get used to. So the thing that we're trying to explain, why objects fall to the ground, right? Um, called the explanandum, right? And that's just Latin for the thing to be explained. Um, and then the explanation itself that you give is called the explanans. So that's the explaining in Latin. Um, so the explanandum, right, the thing we want to explain, sometimes it's a particular event. So why does this particular piece of litmus paper uh, turn red when I dip it in orange juice? Or the thing you want to explain could be a more general pattern. As we said, why do things fall down instead of up? Okay, so given that background of roughly what we mean by scientific explanation and this important terminology of explanandum and explanans, we'll talk about one of the more influential accounts of what a good scientific explanation should look like, and it's known as the deductive nomological account, and it comes from Hempel and Oppenheim. Um, we already read Popper, right? His falsification and his account of science's deductive reasoning. And this deductive nomological model of explanation is going to fit quite nicely with Popper's thinking because it does involve deduction, right? That's the deductive part of deductive nomological. So the claim there is that explanation consists in deduction. So I can explain a phenomenon if and only if I can deduce it from a set of premises. And the set of premises is the explanans, right? That's the explanation. So this means that explanation will take the form of an argument in deductive logic. You will have premises and you will have a conclusion that's deduced from the premises, and that is the explanation and the thing to be explained, right? So that's the deductive part of the deductive nomological model. What's the nomological part? Um, Nomos means law, right, in Greek. So nomological means having to do with laws. And what Hempel and Oppenheim say is that one of the premises in your argument, in your explanation, right, needs to be a law of nature for your explanation to count as a scientific explanation. Certainly, when I explain that I was late because there was traffic on the 5, it's not a law of nature that there will be traffic on the 5. Um, so that's one reason, among probably many, that my explanation does not count as a scientific explanation. Okay, so since we've started with this falling down, not up, right? So I dropped my phone. What was it? Right. So here I'm talking about a stapler. I don't have a stapler handy. But so why did the stapler fall down towards the earth and not towards the ceiling, right? Here's our why question. What's our explanation? Well, we do have a law of gravity, right? It states that, or Newton has a law that states that matter exerts an attractive force on other matter, right? And it's that force is going to be directly proportional to its mass and inversely proportional to the distance between. So as objects get bigger, they attract each other more, and as they get further away from each other, they attract each other less. And it can be symbolized in this equation right here. So the force is equal to the gravitational constant, which is g, multiplied by the masses of the two objects, and divided by the radius squared. In addition to the law of gravity, you need a few more things, and these are called antecedent conditions. Right? You can plug into the equations, right? So these equations are just variables. So I'd need to know the mass of the Earth, the mass of the stapler, the mass of any nearby objects that might exert a competing gravitational force on the stapler, and the distance, right, between the two objects. And so in English, right, this deduction could happen mathematically, but in English, basically the argument is, well, look, the Earth has more mass than the ceiling in this room and the other objects in this room. Um, and other objects like the sun, which are more massive than the Earth, are way farther away. So if you plug all those conditions in, right, and you do the math, you'll find that the Earth exerts the strongest attractive force on the stapler, and so the stapler is going to move towards the Earth. Okay, so you'll notice that I didn't actually put this in like a argument form, right, with the premises and the conclusion. Hempel and Oppenheim claimed that in principle it could always be done, um, but for me to do it here for even a relatively simple explanation would actually be really, really complicated and hard to follow. So an interesting question whether that's a problem for the DM model, right? But you're not going to see very often people actually producing these supposed arguments that are the explanations. Okay, one more example, just sort of to get the idea. You can never have too many examples. Um, and this comes up in the Hempel and Oppenheim. So why does a stick placed in water appear bent? Here in the photo, we see, right, a pencil, you put it in water, and it looks like the pencil is at an angle. Well, we do have a law of nature, right? Snell's law, which relates the angle of incidence and the angle of refraction of light passing from one medium to another. And you need the refraction indexes of those media. So here you have the ratio between the sine of the two angles, and those are equal to the ratio of refraction indexes. So water has a particular refraction index. Air has another one, right? So that this pencil is passing from air to water, and so is the light that's reflected off of it. And so those indexes are going to determine the angles that you see, right? Angles that the light bounced off of, and when it hits your eye, it's going to form an image that matches those angles. Okay, so we had that law of nature. Of course, you do need some antecedent conditions to plug in. You need the actual refractive indexes of air and water, 1.0003 and 1.33 respectively. You need to know the position of the observer. There's actually also going to be a lot of laws involved in the human visual system, right? If we're talking about appearances, so you need quite a few laws, right, that run from the eyes through the neurons to the areas of the brain, and so on. But in principle, right, you could deduce the appearance of the stick from that collection of laws and antecedent conditions. So I believe this is a quote from the reading on the deductive nomological model. Why does this phenomenon happen? Means according to what general laws and by virtue of what antecedent conditions does the phenomenon occur, right? So that is explanation and a deduction from laws and now you could keep asking, right? Philosophers and young children like to ask why to every answer you give them, right? So um, I gave you those laws and antecedent conditions as an explanation. You might then say, well, why is the refractive index of water what it is, right? Why is the why is the ratio of the angles equal to the ratio of the refractive, and so on? And that's fine for Hempel and Oppenheim. They say, sure, you can keep asking why. You can explain laws, right? You can ask for explanations of laws, and that will be typically. So over here on the right, I do have sort of a diagram uh, to explain it. Have to get into physics, right? The nature of the particles that make up air and water, the behavior of the electromagnetic waves that are light, and so on. But they do intend for the deductive nomological model to be a completely general kind of explanation. You can keep going back. You can explain laws that explain laws that explain laws that explain laws, right? And if they're right, this means that in principle, every phenomenon worth explaining could be deduced from the laws of nature and antecedent conditions. So you may have noticed that if you had the explanons, if you had these antecedent conditions and the laws, you should, and you didn't know necessarily what the outcome would be, you could, in principle, predict the explanandum, right, just by doing your deduction. Um, so if I gave you Newton's laws and the antecedent conditions and asked you what will happen when I let go of the stapler, right, you could do the calculations and deduce that it's not going to be attracted by the ceiling, right? That it's not going to be attracted by the sun as strongly as it'll be attracted by the earth, and so you can predict it's going to hit the earth. Um, Similarly, you could predict the appearance of the pencil, right? If you had all these laws and antecedent conditions. So importantly, then, the deductive nomological model says that explanation and prediction are two sides of the same coin, right? They're both deductions. So if you read the article by Hempel and Oppenheim and were a little confused when they get into some of the more formal statements of their account, here we'll go over it uh, briefly so that if you were to look back at it, it'll make sense to you, or if you haven't read it yet. So here we go. Formal definition of the deductive nomological model of explanation. An explanans, right, the part that does the explaining, consists of two classes of sentences. So we have antecedent conditions, like we noticed. So that's symbolized by C1, C2, C3, on to CK, whatever that, whatever the last number is. And then a set of laws, law 1, law 2, law 3, so on. Law I, or law, an R. Anyways, the last law that you use. Okay, so that's the explanation, right? The premises of the argument, which consists of those two types of sentences. And in order for the explanation to be sound, these sentences need to fulfill two types of conditions. You'll have logical conditions and empirical conditions. First, the logical conditions. The explanandum, the thing to be explained, must be logically deducible from the explanans, right? So this we've already stated. This is the D, the deductive part of the nomological model. Another requirement is that the explanandum must contain at least one law. We already mentioned that as well, and this is the N, the nomological part, the DN model. Now, importantly, that law also has to be an essential premise, right? So what that means is if you took that out, the deduction would no longer be valid, right? And that's important because you don't want to be able to just plug an arbitrary law into the premises and say now it's a scientific explanation, right? So I shouldn't, if you ask me why I'm late, and I said, oh, there was traffic on the 5 and um, force equals mass times acceleration. That shouldn't be a good explanation just because I threw a random law of nature in there. So it might be the case that the explanandum consists only of laws, right? So there might not always be antecedent conditions. This is most likely to happen when you're trying to explain the laws themselves, right? Because you're doing more abstract theoretical stuff, and it's going to be more variables, right? That produce other variables. Okay, third condition: the explanans must have empirical contents, and again, this is the explaining part, right? That is, it must be testable, right? At least in principle. Um, So this is an important difference between scientific explanation and sort of everyday explanation, some kinds of pseudoscience like astrology or something, right? So you take a conspiracy theory. Um, so, right, if you want to say that humans never landed on the moon, um, and every piece of evidence to the contrary, you explain by saying, oh yeah, well, that was planted by conspirators, right? Um, that kind of entails that there's no piece of evidence at all that I could ever produce that would convince you otherwise, right? So your theory is not falsifiable, right? There's no experiment that could possibly prove it wrong. If that's the case, then Hempel and Oppenheim are going to say that your explanans doesn't have empirical content. So another way to say this is like, along with Popper, they think that important distinction between science and non-science is that the theories are falsifiable, right? So there has to be some kind of empirical test that could prove it wrong. Okay, and here, so those were, here is an empirical condition of adequacy. Um, so the sentences constituting the explanons must be true, right? So it seems sort of obvious, right? For a deductive argument to be sound, the premises need to be true, right? And uh, my explanation, if you ask me why I'm late, and I said, oh, an elf sort of got into my engine, a gremlin got into my engine and messed it up. That's not going to be a good explanation because it just didn't actually even happen, right? So even if it were true, right, you could do the deduction. It's not going to be a valid inference, or it will be a valid inference, but it's not going to be a sound argument if the premises are false. You need both. You need a valid deduction from true premises. But here we sort of get into a little uh, weirdness, right? Because remember, according to Popper, you never say that your theory is true, right? You would never say that your hypothesis is true. At best, you would say it's corroborated. Hasn't been proven false yet. You may remember that from the part on falsification. And Hempel and Oppenheimer are aware of this, and they like Popper, and but they're worried that if you didn't insist that the premises in your explanons were true, and say, okay, we'll just say that they're sort of corroborated, then you run into the problem that in the past we've had theories that are false that at the time were corroborated, and right, you could deduce um, phenomena from those, right? But we don't want to say a false theory is a good explanation, right? So, for example, once upon a time, you can see in this picture, the way people thought heat worked was that it was of some kind of substance, right? And it would like move from hot stuff into cold stuff, or vice versa. It would reach an equilibrium. So we now know that in fact heat is particles moving really fast. Right? The faster the particles move, the hotter it is. The slower they move, the colder it is. So the theory of caloric is wrong, but you can certainly right create an argument and deduce the phenomenon from a theory of caloric, right? So I could put my kettle on the flame and the water boils. And I could say, oh yeah, the caloric went from the burner into the water. And that certainly would be a deductively valid argument, but it would not be a sound argument because the premises are false. And if I weaken that corroboration, then I would have had to say, if I had given that explanation back in 1700s, I would have had to say, yep, that's a great, perfectly good scientific explanation, caloric, right? And they don't want to say that, right? So they have to insist that the premises are actually true. So here is a diagram from the reading of the DN model. So we have C1 through CK. These are the antecedent conditions. We have our laws, and that line means we have a deductive argument that gives us our explanandum, right? Um, okay, so back to explanation and prediction, right? Um, we noted that these explanations can be used to predict, right? If you have the explanons, I could deduce whether the phone or the stapler will fall down or up before I even drop it. And in fact, Hempel and Oppenheim claim that an explanation is only adequate if it can be used to predict the phenomenon or could have been used prior to the phenomenon's happening. So they're going to say explanation and prediction are basically the same thing. If you can't predict, you can't explain. And again, this is very important if you're sort of in generally a Popper type person, because a theory is only as good as its predictions, right? The point, what makes a theory a scientific theory is that it makes predictions that can be falsified. This is the whole practice of science, is we take those predictions and we determine whether they're true or not. So for Hempel and Oppenheim, the predictive power is part of the explanatory power. And really, they say there's only a kind of a pragmatic distinction between the two, between prediction and explanation, just sort of like at what point in time you did the explanation, right? If you do it before the thing you're explaining, then it's a prediction. If you do it after, then it's not a prediction, but it's still an explanation. But they don't think that's really that significant if you're talking about the essence of explanation. And this is important, right? Because explanation helps us to understand the world, prediction helps us control the world, right? And that's what gives explanation its power. All right, there's a distinction between scientific and everyday explanation. Um, so Hempel and Oppenheim do want to say there is a distinction to be made. Um, so you might want to explain why you got in a car accident by pointing out that you blew a tire. Um, but you couldn't predict an accident on that basis, right? Just because I have in the past blown tires and not gotten into accidents, right? I have just sort of pulled over the side of the freeway and been fine. So just that bit of information wouldn't allow you to predict the accident, and so they're going to say that's not a sufficient explanation, right? Even though probably, possibly in the everyday sense of explanation, um, if right, if a cop shows up to the scene and they ask me to explain what happened, I say, oh, I blew a tire and I skidded out, and blah, 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 and that might be sufficient for them as an explanation, but it wouldn't be sufficient as a scientific explanation. It wouldn't be sufficient for prediction. Um, and sometimes in everyday life, we also use identity statements as explanations, right? So if somebody says, "Oh, did you see that? It looks like that star just fell out of the sky," or you notice a shooting star, and you say, "Oh, yeah, those are comets," right? And people might say, "Oh, I get it," right? So um, identity state, or right? Oh, the North. Did you know that the morning star and the evening star are actually the same thing? They're Venus, right? Um, People might go, "Oh, now I understand," right? And so in a sense, you're explaining, but that's not good enough for Oppenheim for scientific explanation. In particular, you need a law of nature involved there, right? None of those explanations was there a law of nature involved. But you might think you could argue, they leave it open, right? That you could argue that scientific explanation and everyday explanation actually are the same kind of thing, but what happens in everyday explanation is we leave a lot of stuff out, right? That if pressed, we would say, oh, well, yeah, there's more to the story, right? Um, Go back to the example of, right, my accident with the blown tire, right? If you ask me to explain why I ran into if I got in an accident, I say, oh, I blew a tire. But if you pressed me and said, well, haven't you blown tires before and not getting in accidents? Certainly, blowing a tire isn't the only factor involved. I might say, oh, well, yeah, you're right, I guess. There's also the fact that there was another car going at a certain velocity, that I was going at a certain velocity, right? And and that I lost control of the car because of such and such, right? So if pressed, even everyday explanations, right? People might uh, actually concede that, well, a full explanation would basically be a scientific explanation, right? And I'd have to invoke sort of laws about the pressure of the air in the tire vis-a-vis the strength of the rubber, what caused the blowout in the first place, the forces and trajectories of the cars. So you might argue that all explanation is scientific explanation. We just, in everyday cases, we leave some stuff out. So there's an interesting um, connection between causation and explanation, right? Um, and this oddness sort of comes out mostly in the Stanford Encyclopedia article, um, where I believe it's Woodward wrote it, right? He talks about kind of at the time, right, when Hempel and Oppenheim were writing, there was sort of a tendency to not want to talk about causation because it seemed sort of mysterious, and this is partly in due to Hume, right, who convinced everyone that you don't observe causation. What the heck is causation? All I see is events following other events. Um, and so they were tended to avoid talking about causation, right? And they wanted to use explanation instead, because you can reduce that to a deductive argument, then we're all on firm ground, right? We know what deductive arguments are, and then we know what explanations are, and so on, right? And if you want to define causation, maybe you define it in terms of explanation. But we won't get really to any accounts like this except in the supplemental readings I gave you, Nancy Cartwright and stuff. Um, some people want to talk about explanation in terms of causation. This is what I just said. Okay, and here Hempel and Oppenheim just want to sort of point out that their account of explanation doesn't just apply to physics. Um, so here uh, on the right, this is Fechner's law, which is a law in psychophysics, the study of perception, right? And what it says is that sort of the perceived intensity of a stimulus sort of tails off. It's a logarithmic relationship. So, like, you may notice, so if between a coffee with no sugar and a coffee with one sugar, right, to your taste buds, you will notice that. Between 8 sugars and 9 sugars, you might not notice, right? So that's basically what Fechner's law says. Um, there's other laws in psychology, and if laws you can, right, then you can do scientific explanation. Um, now, one important difference between most of these laws in psychology and these laws in physics is laws in psychology and many of the other special sciences, we'll call them, like economics or anything that's sort of less fundamental than physics, um, is there can be exceptions, right? There might be somebody out there that can tell the difference between 8 and 9 sugars, right? Um, so these are tend to be statistical generalizations you'll find in the behavioral sciences and many other sciences. But Hempel and Oppenheim say that's fine, right? And it's not clear, it's sort of up in the air whether the reason that there can be exceptions is that we just don't know enough, and if we, get better psychology, we'll be able to predict people perfectly, or it might be that there's fundamental indeterminacy in nature, right? Certainly in quantum mechanics, that seems to be where we are at the moment. Um, so, but they say that's fine, right? It's not a problem for the DNA. So here in the Hempel and Oppenheim, they use an example from economics, another one of the special sciences. So they say in the fall of 1946, the price of cotton really just dropped a lot, and it triggered a halt on the stock exchange, right? So when prices drop too far to sort of stop things from going haywire, they'll like it kind of triggers like a circuit breaker. Stop trading for a little while. So you might want to explain that, right? Why did this happen? Well, there were antecedent conditions, right? So there happened to be one really big investor who decided to liquidate his cotton holdings. Smaller investors caught wind of this, started doing the same thing, and all of a sudden, there's all this supply of cotton, right? And then we've got a law of economics is demand. So if supply rises, right, you got a ton of cotton, and you don't have demand rising accordingly, then the prices are going to go down, right? So thus we can explain, predict this drop in price. Um, you might worry about what about human choices, right? Human motivations. Um, is that the sort of thing that can be explained using laws, right? Or is this human agency something uh, sort of apart from nature, right? That doesn't follow laws. Deep question in metaphysics, right? But Hempel and Oppenheim at least say no, human right choices can also be law governed, and we do have over on the right. I just have some laws of or some axioms of expected utility theory. So this is a an account of human decision making, right? And it's based on a probabilistic calculations that people make based on their right, interests, maximize their utility, um, their beliefs, their desires. So none of this is sort of directly observable, and none of it is some of it, not all of it is predictable with precision, right? There is often exceptions, but nonetheless, um, Hempel and Oppenheim think they'll explain, right? In the same sense, you have laws, you have antecedent conditions, you can deduce the right answer more often than not. Fine for okay. So they sure right this the N in the DN account of explanation um, leans heavily on there being laws, and you might wonder what the heck is law. So Hempel and Oppenheim talk about it a little bit. We're going to spend a whole week on it next week. Real briefly, they do say a little bit about what counts as law and what doesn't. So what you want to make a distinction between laws and accidental generalizations, right? So there's statements that just are true, right? Even general statements that are true, but you don't want to say that they're laws of nature. So um, it is true that everyone in this room that I'm in is shorter than 6'4". And from that generalization, we could then deduce that Nate is shorter than 6'4". But that's a terrible explanation of why I am shorter than 6'4", right? Um, the real explanation would have to do something with genetics, right, and the heights of my parents and so on. So this is right. That's why a good explanation has to have a law of nature, and a law of nature is going to be more than just some true generalization. Um, but we'll see next week that while this is one part of what we want to say, we want to capture laws, there's a lot more to be said about laws. A serious problem we need. Okay, so that is the lecture on the DM model explanation. And next, we'll talk about some objections. All right.